Okay, in this video we are going to be looking at the redox electrical potentials of the electron transport chain. Now, movement of electrons in the electron transport chain is a very unique chemical reaction. Up to this point, we've been talking about chemical reactions and free energy changes. We talked about the fact that in a chemical reaction, a positive free energy change, delta G, is unfavorable, and a negative delta G is typically what we prefer, which is a favorable reaction. The reason for this is because we are giving off energy in the reaction, so this is an exothermic versus an endothermic, which requires the input of additional outside energy, making it unfavorable. Now, when we're talking about movement of electrons, electron movement is measured in voltage. A little different than free energy changes. We'll connect these two later on at the end, but what we need to look at first is a little bit of physics and talk about voltage. So recall our equation of voltage. Voltage equals current times resistance. Now, in this case, the voltage is considered a pushing force. So think of voltage as the push behind the electrons. The higher the voltage, the higher the pushing force. We know this intuitively because if we look at our 120 volt electrical outlet in our home and compare this with a battery of 12 volts, the electrons that come out of here will give us a much greater shock than coming out of the battery. And the reason for this is because of this pushing force. So the higher the voltage, the greater the electron movement. Now, as far as the electrons moving in the electron transport chain, the best way to examine this is the standard potential values, which are E 0 prime. So this is the change, the standard change of an the electrical change, standard potential change of a particular reaction. So let's look at each one of the complexes in the electron transport chain. So we know that NADH is giving off electrons. These electrons move from complex 1, which is the NADH dehydrogenase. This will move to CoQ. The electrons then from CoQ move to complex 3. From complex 3, they move to cytochrome C, and from cytochrome C, they move to complex 4. Now, this electron movement has to occur in this path. The reverse cannot happen, because if the reverse happens, we will not be generating the proper electrical potentials here in order to generate our electrochemical gradient of protons to generate ATP. So the question is what makes this a singular direction, a unidirectional movement of electrons? Why can't they go back? Well, let's look at the reactions individually. So in complex 1, the reaction we were looking at here is NADH plus H, giving off the electrons, NAD plus 2 protons plus 2 electrons. So this is the job, the function of complex 1. Now, if we measure the standard electrical potential change of this reaction, we will have a positive 0.32 volts. Now recall up here that voltage equals pushing force, so the fact that we have a positive voltage means that this is a favorable reaction. Now, the next step for complex 1 is to take this reaction and bring this to CoQ. So that particular reaction, in order to reduce CoQ, is going to be CoQ plus 2 protons plus 2 electrons. Here's our electron movement. And we are going to have a reduced CoQ. So these two reactions written this way is the redox reaction occurring between complex 1 and CoQ. Now if we look at the standard potential change of this reaction, we see that it is a positive 0.05 volts. So what this means is that moving electrons from NADH onto complex 1 and then from complex 1 to reduce CoQ, this is also a favorable reaction because we have a positive voltage pushing force. Now, from this point, let's look at complex 3. For complex 3, we have the reverse reaction. We are going to have CoQ in its reduced form, and this is going to become CoQ in its oxidized form. So the standard voltage potential of this is now going to be the reverse of this, negative 0.5 volts. Now let's look at the complex 3. So complex 3 will be receiving the 2 electrons. So it starts out in its oxidized state, and it is going to be in its reduced state. So what is the standard potential of this reaction? Positive 0.08 volts. Now how do we determine if this reaction will move forward? Again, very similar to what we did with standard free energy changes on our chemical reactions, we are going to add these two together. And in this case, we get a positive 0.3 volts. So what this says is the movement of electrons from CoQ to complex 3 is a favorable reaction. Now, let's take a look at the movement of electrons to cytochrome C. So in this case, we must oxidize complex 3. So complex 3 will begin in its reduced state, and we will now reverse the reaction because we are now oxidizing to give off these electrons. So this is going to be a reverse of the standard potential we saw above here. So this is going to be a negative 0.08 volts, indicating that this is not favorable. But what's going to drive this reaction is the reaction with cytochrome C. So cytochrome C, we add these electrons. We're going to reduce the cytochrome C. And let's examine the standard potential of this is positive 0.25 volts. So now, again, like we did above, how do we determine if the movement of electrons from complex 3 to cytochrome C is a favorable reaction? We make sure that our equations are written in the proper orientation, and then we add the voltage potentials. So this voltage potential will be 0.17 volts. Again, this is favorable. Now our final step is the reduction of cytochrome C, sending our electrons to complex 4, which of course is going to put the electrons on water, on oxygen to make water. So to draw this reaction, we need to do cytochrome C begin in its reduced state, and the cytochrome C then is oxidized to give off these 2 electrons. The standard potential for this reaction, of course, is the reverse of this. So this is a negative 0.25 volts. So this is an unfavorable reaction. However, when we look at the reduction of oxygen, to form water, the standard potential of this is a positive 0.82 volts. So again, in order to determine if the reaction of moving electrons from cytochrome C through complex 4 and ultimately onto oxygen to generate water, is this favorable, we just add the standard potentials together. And what we see is a 0.57 volts. Again, favorable. So the important take-home message of this here is to look at the redox reactions written in their proper sequence and then write out the standard potential for each of the reactions, add them up, and determine if the movement of electrons from each of the complexes or electron carriers to the subsequent carrier is favorable or not. And what we see when we do all these calculations is that each reaction is favorable. Because of this, this gives us our directionality into the electron transport chain. This makes the electrons move from complex 1 ultimately to oxygen to form water, and this direction is not reversible. Now, the whole purpose of this is, again, to generate the proton gradient across the inner mitochondrial membrane. Recall that complex 1, complex 3, and complex 4 are involved in pumping those protons from the matrix into the intermembrane space. The pushing force, the change in voltage, is going to be converted into energy to do this reaction. So what we are generating ultimately is what's called the proton gradient, which is called proton motive force. And the proton motive force is simply due to the pumping of protons by these complexes because of the drop in energy state due to the electron movement. And what we will have is a very high concentration of protons in the intermembrane space and a lower concentration in the matrix. So this is a chemical gradient because we have a small atom here of a different concentration on each side of a partition, the membrane. And it's also an electrical gradient because protons are charged. And so now we have a displacement of positive charge, higher concentration in the intermembrane space. This gives us our proton motive force. Now, in order to determine the energy of this, we have to examine the free energy change of the electron movement. So how do we convert electrical potentials into standard free energy changes? We are going to look at the standard free energy change of the reaction is going to equal negative n. N equals the number of electrons that are being moved times the Faraday constant times the change in standard potential. So this is the way to convert standard electrical potentials into free energy changes. Now, let's just do this for the entire electron transport chain, starting from the beginning. So if we start from the beginning, we have NADH being oxidized to NAD, and we saw that the standard potential of this is a positive 0.32 volts. Now, if we want to examine the entire electron transport chain without concerning ourselves with each intermediate step, all we have to do is go to the very end reaction, which is the reduction of oxygen. So we are essentially saying we are taking these two electrons from NADH and ultimately we're transferring them to oxygen to create water. We saw the standard potential of this reaction is a positive 0.82 volts. So if we want the standard potential of the movement of electrons from NADH ultimately to oxygen to generate water, we simply have to add these two together. And this gives us positive 1.14 volts. So essentially, this is the voltage difference across the entire electron transport chain. Now, the pumping of protons requires energy in the form of work. This voltage change here across the entire electron transport chain is the energy driving this process. So now, if we want to check what the standard free energy is of this reaction across the electron transport chain, all we have to do is plug in some numbers. So in that case, the standard free energy change of the electron transport chain measured in delta G is going to be a negative 2 because we're moving 2 electrons. This is going to be times the Faraday constant, which is 96,485 joules per volt per mole. And this is going to be times our standard potential change, which is a positive 1.14 volts. If we do our calculation here, the standard free energy change becomes negative 220 kilojoules per mole. So this is the relationship of the standard free potential change, electrical potential, compared with the free energy change. So now this ties together the fact that the positive voltage change seen across the entire electron transport chain shows the amount of pushing of electrons. It shows in the previous page that we Each successive step is a positive voltage push to make sure we have a unidirectional movement of the electrons. And if we look at the thermodynamic calculations of this movement, we see that the standard free energy change is minus 220 kilojoules per mole. Another way to look at that in its relationship to the pumping of protons is if we look at free energy on our y-axis, and on our x-axis we look at our reaction coordinates like we have seen before, we will see, now we're measuring delta G, recall here free energy changes, we are having successive changes in free energy down the electron transport chain that are all negative. So this could be considered the free energy state at complex 1. This would be considered at CoQ. Here's complex 3. Here's cytochrome C. And ultimately here is complex 4. So we are decreasing our free energy state, making each successive redox reaction is a favorable reaction. Now what about, how does this relate to the pumping of protons? Well, we know here that complex 1 pumps 4 protons. Where does it get the energy? Right here. The energy difference between complex 1 and CoQ, measured in free energy change, is negative. So this negative free energy change, this giving off of energy, exothermic reaction, is causing the conformational change in complex 1 to pump 4 protons. What about complex 3? Well, we saw complex 3 pumps 2 protons. Where does it get the energy from that? Notice the change in free energy is negative between complex 3 and cytochrome C. This negative free energy change, exothermic reaction, that energy is being harnessed by complex 3 to pump those 2 protons. And finally, complex 4 pumps 4 protons. Where does that energy come from? Well, consider the fact here that we are forming water. This difference between the electrons moving from complex 4 to water is giving off free energy. That energy is harnessed again, similar to before, by complex 4 to pump the 4 protons. Now ultimately, once we form our proton gradient here, our electrochemical gradient, we are going to want to dissipate this gradient now that we've established it. And again, this is our ATP synthase complex. So recall we have a very high concentration of protons in the intermembrane space. We have a lower concentration in the matrix. And so this gradient we are going to use in order to generate movement in our molecular motor. So the dissipation of this gradient, which is stored energy, will be transformed into kinetic energy of spinning this molecular motor. Now, this energy of kinetic energy being changed, causing this movement, will be harnessed by this enzyme complex to generate ATP. So the best way to look at this is that if you have 3 different sites on your head of the group here, let's say, for example, that ADP binds to one site along with inorganic phosphate. Now the movement of protons is going to spin this head, so this head will start to begin to turn. Once this head turns, now we've moved the head into a different position, And this process here is going to generate our high energy bond. So we've taken the kinetic energy here and we've put that into forming a high energy bond to generate ATP. Now this head spins, continues to spin, and then the final step would be the release of ATP. Now the next step of the reaction, we spin the head back to its original position where it binds ADP plus inorganic phosphate again. Once again, the head begins to spin, converts that energy into creating the high energy phosphate bond, generating ATP. The head spins again, releases the ATP by dissociation, and then spins again back into its original position to bind more ADP plus inorganic phosphate.